Now we will see PN junction diode formation. Now we are entering into the electronic device concept, that is a PN junction diode. So already we know what is P type and what is N type. Those two should be taken here. This is P type and N type material also I am taking here. Otherwise, people will take one intrinsic semiconductor, diffuse pentavalent impurities from this side to create N type and diffuse this third group elements doping process this side, then P type will be created. But we know that in the P type, holes are many. So negative charge, negative ion with positive hole, I am representing like this. This is a negative ion with this plus is indicating hole because hole is the positive charge carrying. Okay, like this I am taking. But these are majority. Minority are also there. Those are positive ion with electron. This is about P type. Now in the N type opposite we have to take positive ions with electrons are majority. And negative ions with positive holes are minority. So like this we can able to take. So when you take P type material, N type material, this is the initial stage. But after that what will happen? After that what will happen means here diffusion process will be done. Because in this region holes are many and in this region holes are very low. I am talking with respect to holes in the beginning stage. This is the region where holes are very high. This is the region where holes are very less. So here holes, all are holes only. 1, 2, 3, 4, 5, 6 I have taken. But here only one hole is there. So here holes are many, here holes are less. Water is flowing from higher level to lower level. Current is flowing from higher potential to lower potential. Here holes are also moving from higher number to lower number. So hole I am indicating like this. This is also hole. Hole is moving from P side to N side like this. Hole is moving from P side to N side. That means here holes are moving from P side to N side. That means left side to right side means here only these negative ions are created. These holes are moving, but negative ions are not moving. These ions are fixed, but charge carriers holes will be moved. So here negative ions, we will be leaving with negative ions at this particular junction. Now we will talk with respect to electrons. Here free electrons are very less. Electrons are very less. But here electrons are very high. Because it is N type, electrons are high. Again same thing. From higher concentration to lower concentration, electrons are moving. So electrons are moving from N side to P side. Electrons are moving from right to left. So that here we will get only positive ions. Ions are not moved here. So positive ions are created without electrons here. So electrons are moving this side, holes are moving to this side. So this is the hole moving from left to right and electron is moving from right to left. So those two will be combined. So what is the resultant diagram is nothing but here I am taking. This is the junction where P type and N type are joined. So here you will get negative ions without holes. Here you will get positive ions without electrons. Okay, but remaining are with negative ions with holes will be there. And minority are positive ions with electrons. And here positive ions with electrons are majority. And this is negative ion with the hole. Now near the junction if you observe, without any holes you will get here negative ions. Negative ion layer is created. And without electrons here one positive ion layer is created. So near the junction here you got negative ion layer left side, positive ion layer right side. These layers are without charge carriers. Okay, these layers are involving the only ions without charge carriers, either holes or electrons. So this is called depletion region or space charge region. Space charge region. Okay, this is called depletion region or the space charge region. As the process is going on, this process is called actually diffusion. Movement of the charge carriers from higher concentration to lower concentration is called diffusion. The diffusion process has been done for holes from p side to n side, and for the electrons also from n side to p side. Because of the diffusion process, here you are observing the negative ion layer at the left side of the junction and positive ion layer at the right side of the junction. This entire region is called depletion region or space charge region. The width of this depletion region is indicated with W. So this is what we can able to observe. Like this, the p-n junction diode has been created. Now, further, we can able to take the diagram once again to know about the charge density relations. So I am not trying everything, just I am concentrating on this depletion region only. This is the width of the depletion region. Okay. Using the Poisson's relation, that is del square V is equal to minus rho V by epsilon, I am taking. Again, del is a vector differential operator related to three directions x, y, z, but I am concentrating only on the x direction. So it will become only one with respect to one variable only. Dou square V by dou x square is equal to minus rho V by epsilon. Rho V is the charge density. So here outside this junction, the net charge is equal to 0 because every negative ion is with the positive hole. Here every positive ion is with the electron. So net charge is 0 out of this particular junction, out of this particular depletion region. Okay, this is exactly where the two n-type and p-type are meeting. So if you take this left side to this particular junction, here negative ion layer is there. So negative charge is there. That is what we can able to take. That negative charge also, if you take uniform negative charge, okay, it is in the x direction. That is what I have shown. Okay, it is a step. Uniformly, it is available from here to here. But once you are entering into this side, then here positive ion layer is there. So positive charge we have to take like this. Positive charge. That is nothing but above the x-axis. Below the x-axis I have taken here because here negative charge is there and here positive charge is there. And outside of this junction, outside of this depletion region, no charge. That is what we have taken. So this is representing the rho V. This is representing the rho. That is what we need to understand. Now, we know that electric field is negative of gradient of the potential, or we can tell minus dou V by dou x. Okay, when you consider only one direction. So if you do, it is the double derivative of the potential. Okay, rho V is nothing but dou square V by dou x square. The double derivative of the potential is there. You need single derivative of the potential to get the electric field. So what you need to do? You need to perform the integration of this one to get this. So integration of this one, if you perform, 0 is there here. So here also you will get 0. This is negative step. That means a negative ramp you will get. Again the positive. That means it is increasing. So like this you will get. Outside 0. Okay. So this is nothing but electric field graph within this particular junction. So in the depletion region, you are finding the potentials are like this. Okay. Second derivative of the potential, it is the first derivative of the potential you are getting like this. And potentials also you can able to get up by performing one more integration to this one, because integration of this one will give the potential. Okay. So like this you can able to understand about the PN junction. Now we will see current equation. Current equation of PN. I is equal to I naught into e power V by eta Vt minus 1. It is a current equation. First of all, we need to know how the diode can be biased. At the same moment, I am taking biasing of the p-n junction diode also. Biasing of p-n diode. So diode symbol we can take like this. There is a reason for taking the diode symbol like this. It is p side, it is n side. Okay. So this arrow is indicating there is a current flow from p to n only. That is the meaning of this one. This obstacle is indicating there is no current flow from n to p. Current is from p to n. No current is from n to p. That's why this vertical line symbol has been given. Now biasing of the p-n junction diode is nothing but, if you take the p-n junction diode like this, we can give the external voltages. Biasing is nothing but providing the external voltage simply. Biasing is nothing but providing the battery, providing the external voltages to the electronic device in such a way that that is operating in the desired manner. Because it is having the two terminals, in how many ways you can able to give the battery? You can give the battery in such a way that one way is nothing but Vp is greater than Vn, second way is Vp is less than Vn. Only two ways are possible. So for example, if you take Vp is the potential available at P side and Vn is the potential available at the N side. It is Vp, it is Vn. In only two ways you can able to give. One is Vp is greater than Vn. Second one is Vp is less than Vn. So when you take Vp is greater than Vn, that is called forward bias. When you take Vp is less than Vn, that is called reverse bias. These are the two ways of biasing for the PN junction diode. When you are taking the forward bias, this equation is valid. This is the current flowing through the diode. Okay, so this is for forward bias. And if you take the reverse bias, so only I0 is the current flowing through the diode, that is reverse bias. It is very small. It can be in the microamps or it can be in the nanoamps. So diode current equation means simply you can tell this equation, that is I is equal to I0 into e power v by eta vt minus 1. And what are all the letters we have taken in this particular expression, I will tell later. First we will see about biasing, forward bias and reverse bias. So if you take forward bias operation, here we have depletion region and here we have so many holes. So simply holes I am taking and 2 electrons I am taking because electrons are minority here. Here electrons are majority and holes are minority. Okay. Now I'm going to give the battery to this one in such a way that it is going to the forward bias. So it is positive negative. Positive is connected to P side, negative is connected to N side, then we can tell it is under forward bias. Then what will happen is holes are positive charge carriers, but positive is given, repulsion is there. So holes are moving from P side to N side. So hole current is also from P side to N side. Then this N side is connected to negative side. So N side means majority are electrons. So electrons are negative. It is also negative. Repulsion is there. So electrons are moving from N side to P side. But electron current is from P side to N side only. This is very important point. See carefully. Generally in the electrical circuits also, the conventional current direction is opposite to the actual current direction. Like that we will tell. What is the reason for that? Means electrons are of negative charge carriers. Here we are dealing with both type of the charge carriers. Because hole is positive, in which direction hole is moving, in that direction only hole current also should be available. But electron is a negative charge carrier, in which direction electron is moving, for that direction opposite way we have to take the electron current direction. So overall if you see, hole current and electron current both are in the same direction. Holes and electrons are moving in opposite directions, but hole current and electron current both are in the same direction. So same direction means total current will be addition of these two, electron current and hole current. That is why here current is more, and this current is due to majority charge carriers only. What are the charge carriers are flowing through the diode, majority or minority? Majority. So that I can tell here current is in the milliamps. It is large current. And this current is due to majority charge carriers. What is happening to minority here? Minority are electrons attracted towards the positive terminal, minority are holes attracted towards the negative terminal. So here charge carriers are moving through the diode are majority charge carriers. So that's why more current is possible. Okay. And here one more point. Just if you apply the voltage here, positive voltage, is it enough to get the current? Means no. What is the reason for that? First of all, these charge carriers should cross this particular potential barrier. A depletion region is there. This depletion region is to be overcome by the charge carriers. For that, it will take certain amount of voltage. For the silicon diode, if you apply 0.5, 0.4 volts, then it is not enough to get the current. You should apply more than 0.6 or more than 0.7. If you apply the external battery voltage, which is more than the 0.7, then only these holes can able to cross the barrier, these electrons can able to cross the barrier. From that point onwards only current will be started. That voltage is called knee voltage or cut-in voltage. Here voltage and current expression graph if you take, You are starting the forward bias voltage 0.1, 0.2, 0.3, 0.4, but you are not getting the current. So once you are crossing the cut-in voltage or the threshold voltage, then only current will be started. So you need to cross this voltage. Crossing this voltage is nothing but these charge carriers are crossing the depletion region. That means till here depletion region is available. That means width of the depletion region is available. But after that depletion region will become 0. Width of the depletion region is becoming 0. So that current is possible, and current will be in the exponential manner in case of the forward bias of the diode. But when you take the reverse bias, what will happen? You see here positive charge carriers, here negative ions are there, and here positive ions are available, and here electrons are majority, these holes are minority. Now I am giving the reverse bias. Reverse bias means P is given to negative and N is given to positive, like this I am giving. So because of this one, what will happen to majority? First we will check. So holes are majority attracted towards the negative terminal. Electrons are majority attracted towards the positive terminal. That is nothing but here majority charge carriers are not moving through the diode. Majority charge carriers are attracted towards the battery. What about minority? Minority are electrons, but here negative is there, so repulsion will be there. So minority charge carriers, electrons are moving towards right side here. Okay. Then what about this one? Here minority are holes. These are repelled by the positive terminal. So holes are moving towards left side. As I said earlier, if electrons are moving from left to right, electron current is from right to left. Electron current is from right to left, that is IN. Here holes are moving from right to left, so hole current is in the same direction. That means IP. So here also both electron current and hole current both are in the same direction. But these are very little amount of currents, and this current is due to this minority charge carriers under the reverse bias. So that we will represent with IN naught, IP naught. This naught is representing the reverse biasing has been applied. So the total reverse saturation current I naught is given by IN naught plus IP naught, but it is very small. It will be in the order of the microamps or it will be in the order of the nanoamps. It is very small amount of current because it is due to the minority charge carriers under the reverse bias. So it is very small and it is constant only, so that the reverse bias characteristics you will get like this, very small amount of current. So this forward bias current is in the order of the milliamps, reverse bias current is in the order of the microamps or in the nanoamps. Very less amount of current will be there. So in the reverse bias, we will get a very little amount of current. In the forward bias, we will get very large amount of current. Large amount of current means that is in the order of the milliamps. Okay. Then now we will see exactly what is this current equation. I is equal to I naught into e power v by eta vt minus 1. So I is the forward bias current. It is derived in terms of the reverse saturation current. I naught is reverse saturation current. It is very small. And this V is a forward bias voltage. And eta is a recombination factor. So eta is equal to 1 for germanium diode, eta is equal to 2 for silicon diode, and Vt is the thermal voltage. Vd is thermal voltage, that is equal to temperature in degrees Kelvin by 11,600. Okay, so if you take temperature is a fixed value, that is a room temperature 300 degrees Kelvin, Vt you will get a number that is 26 millivolts. That is 26 millivolts. So in the questions, if they ask to calculate the current at a room temperature, this Vt value directly you can take 26 millivolts. Okay. Then they may mention silicon diode, you can take any eta is equal to. If they mention germanium diode, you can take eta is equal to 1. So I naught is constant, eta is constant, E is constant, Vt is constant, 1 is constant. So what are the variables here? I and V only. So this equation is giving the relation between I versus V. So V is on the x-axis, I is on the y-axis. So the relation between forward bias current and forward bias voltage is given by this exponential relation. That is what I have done previously. Okay. So equation will give lot of information. Whenever you are observing the equation, you need to see what are the variables, what are the constants. So the relation in between those two variables is given by that equation. That is what you can able to understand. Okay. So because it is not a straight line passing through the origin, not a straight line, not a straight line passing through the origin, we can tell it is a diode is not a linear device. Diode is not a linear device. Resistor is a linear device because V is equal to R into I. Vi, if you take, you will get the relation like this. Straight line passing through the origin. But it is not a straight line passing through the origin. So that we can tell diode is non-linear device. Diode is active element and it is non-linear element. Okay, these are the points you have to remember regarding the diode. Diode is a non-linear and active element. And through the diode, current is flowing from P side to N side only. Current is not equal to 0. And from N side to P side, really little amount of current, approximately equal to 0 current is there. So in one direction current is passing, that is also from P side to N side only. Current is there using this arrow mark I am showing. This arrow is indicating there is a current. Whenever it is under forward bias, there is a current from P side to N side. But from N to P side, there is no current or very little amount of current is there. So I will not allow any current from N side to P side. So this obstacle is there. So that this diode symbol has been created like this. Okay. Then later some important points we can able to remember like this regarding the diode. Diode is active, diode is non-linear, and because of this reason only we can tell diode is acting like a switch. Switch means two conditions are to be satisfied. One is on switch, second one is off switch. So in one direction current is there, that means on switch. So its related equivalent circuit is short circuit. Current is passing means short circuit. In the other direction from N to P there is no current, that means off switch. So we can take it is open circuit. So if you take the ideal diode, it should be replaced with short circuit whenever it is under forward bias. If it is ideal diode, it should be replaced with open circuit in the off switch case, that means reverse bias case. So on and off is nothing but we can able to tell it is a switching operation. So diode can be using as switch. It is the application of the PN junction diode, switch. Okay. Then biasing means you no need to consider always like this only. It is about forward bias I have given and it is about reverse bias I have given. So forward bias means you should not think that always the positive terminal of the battery is connected to P side, negative is connected to N side. It is not simply the forward bias. It is just one of the cases of the forward bias. The forward bias can be created using the two batteries also. You can take here like this with the 3 volts, you can take here ground, or you can take 3 volts, 0 volts, 3 volts, minus 3 volts, minus 3 volts, here minus 5 volts. It is also forward bias only. How I am telling? You need to have Vp must be greater than Vn. That rule you have to follow. What voltages you are applying, that is not important. The voltage at the P side must be greater than the N side, that is important. So 3 is greater than 0, so that it is following Vp is greater than Vn, so diode is under forward bias. 3 is greater than minus 3, diode is under forward bias. Minus 3 is greater than minus 5, here also diode is under forward bias only. So Vp is greater than Vn, so it is under forward bias. Okay, so using two negative batteries also we can able to apply. Otherwise, you can take only one half cycle of the sinusoidal signal and here you can take 0 volts. Now it is forward bias on. But if you apply full cycle and here 0 volts if you apply, then what will you tell? During the first positive half cycle, it is under forward bias. But during the negative half cycle, it is under reverse bias. This case and it is this case. So AC signal also we can able to provide to change the biasing of the diode. To provide the biasing of the diode, not only DC values, so AC values also we can able to provide. But when you apply AC, the condition of the biasing will be changed. Whenever positive half cycle is there, forward bias will come. Whenever negative half cycle is there, reverse bias will come. So same thing you can able to perform for the reverse bias also. Just change the values 0, 3, -3, 3, -5, -3. You will get the reverse bias operation. Okay.